Okay, let's take a look at those practice problems. The first one says, what is the IUPAC name of the following compounds? Remember, we have to find the longest carbon chain. And not only do we want to find the longest chain, we want to find the longest chain with the most what? With the most branches, okay? So the longest chain that I found with the most branches is this one here, which is a 7 carbon chain. And then we should start numbering from this end because then we have 1, 2. We have a substituent at carbon 2. Whereas if we started here, we wouldn't have a substituent until carbon 3. So we're going to do 1, 2, 3, 4, 5, 6, 7. Now notice, if you had started numbering here, 1, 2, 3, you'd still get this. Sorry, you would not get the same answer because that in that case you'd have 2 substituents, whereas the way I've done it, you have 1, 2, 3 substituents. And remember, we want to maximize the number of substituents. So remember, longest chain with most substituents. Okay, so now we have some kind of heptane, and we have, so let's just write down what we know. We have a heptane, we have a methyl group at carbon 2, so we have a 2 methyl, and then we have ethyl groups at carbons 3 and 5, so we have a 3, 5 diethyl. And so we're going to alphabetize according to E and M, right? We ignore the prefix, the di for the prefix. So if we put that all together, we get 3, 5 diethyl 2 methyl heptane. Remember, there's no space between letters, so it's not methyl space heptane. It's just 2 methyl heptane, like that. Okay, next one. There are 8 carbons in the longest chain with the most substituents. So I found it 1, 2, 3, 4, 5, 6, 7, 8, something like that. And we should start numbering up here 1, 2, 3, 4, right? So you have substituents at carbons 3 and 4. If you started numbering here, you'd have 1, 2, 3. You'd have a substituent at carbon 3, but you wouldn't have something at substituent 4 or position 4. So this is the best way to do it. So 6, or the right way to do it, I should say. So that means that this compound is some kind of octane because there are 8 carbons in the parent. We have methyl groups at carbons 3 and 6. So it's a 3,6 dimethyl. And then we have a ethyl group at carbon 4. So we're going to put that together. We get 4 ethyl, 3, 6 dimethyl. And remember, no space between letters, dimethyl octane. Now again, when we have 2 numbers, they're separated by a comma. And when we have numbers and letters, those are separated by a hyphen. Okay, there we go. That's the first 2. The next one is a bicyclic compound. We have 2 rings that are fused together. The bridgehead carbons are going to be this one and this one. You can see that our bridges, if you count the total number of carbons, we have 5, 6, 7, 8. So this is some kind of bicyclooctane. So we could put bicyclo, and then it's bicyclo something octane. Well, you notice that this bridge has 3 carbons, this bridge has 3 carbons, so it's bicyclo 3, 3, and then this bridge has nothing in it, so 330 octane. Now, as far as where do we start numbering, if I put, this bridgehead in yellow and this bridgehead in green, we should start at the one in green because then we can go 1, 2, and have a substituent at carbon number 2. Whereas if we start at the one in yellow, we wouldn't get our first substituent until carbon 3. So we go first substituent, the lowest possible number. So we go 1, 2, 3, 4, 5, 6, 7, 8. So we have a 2, 7 dimethyl. So we'll put that in. We've got 2, 7 dimethyl bicyclo 3, 3, 0 octane. Just like that, 2, 7 dimethyl bicyclo 3, 3, 0 octane. All right, next one, a little bit bigger compound, okay? This one, it might have taken you a while to find the longest chain. The longest chain I found, I won't even highlight it, I'll just number it, was 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And then with that, we have a substituent here, we have a substituent here, and then we have a big substituent here, which contains 4 carbons. And so if we name those substituents, we have a 3 methyl, a 4 ethyl, And a 5, this one is an a sec butyl. So remember, this one here is a sec butyl. Okay, so we have a B for that. Then we have E for ethyl. And then we have M for methyl. And so the sec butyl is going to come first, then the ethyl, and then the methyl. And then if there's 9 carbons, this is some kind of nonane. And so we put the substituents in alphabetical order. So we have 5 sec butyl, 4 ethyl, 3 methyl nonane, 3 methyl nonane. All right, longest carbon chain. It has to go from highest to lowest. Yes. So somebody just asked me the numbers that go in the brackets here. Yes, you always go from the longest to the shortest. Okay. So you go from longest bridge to shortest bridge, always. Yep. Good. All right. Let's keep going. The next one. The next one involves complex substituents. I actually skipped this section on complex substituents, so I'll go over it with you here. But you can see that the parent here is the ring, which is a cyclooctane, right? It looks like an octagon. So this compound is some kind of cyclooctane. But as far as this substituent goes here, we don't have a name for that. There's no common name that we can give for that. So the way that we name a complex substituent is you just find the longest carbon chain, which contains, I'll use red, which has 1, 2, 3, 4 carbons. So this is some kind of butyl group. And then there's 2 methyl groups on carbon 1. So the name for this side chain would be 1,1-dimethylbutyl is how you would call that, dimethylbutyl. Okay, so that's how you name a complex chain like that. Again, I don't even know if I have a question about a complex chain on or a complex substituent on the quiz, so don't stress about those a whole lot. But if you put it all together, you get 1,1-dimethylbutyl. So I'll put it down here, 1,1-dimethylbutyl cyclooctane. Cyclooctane, there we go. All right. The next one, students usually find these are easier. Somebody said list the branches in alphabetical order. Yes, we do. But remember, this is a complex substituent, right? This is a complex substituent, so it all goes together. That, what I have underlined in black, is the name of this entire substituent. Okay? It's the name of the whole thing together, so it's one word. Does that help? Okay. All right, so this is, if you look at complex substituents, that's what kind of substituent that is. All right, the next one, students usually find these actually easier. Questions like these ones here where you have to give the structure for the name. The first one is 3-ethyl-2,4,6-trimethyl-octane. So here's how I would do this. I'd start with the parent. Remember, when your pen touches the paper, that's the first substituent or the first carbon. So 1. So there's a dot. 1, 2, 3, 4, 5, 6, 7, 8. At carbon 3, so 1, 2, 3, we have an ethyl group. At carbon 2, 4, and 6, we have a methyl group, and that's it. That's the whole compound, just like that, okay? The next one is 3-ethyl-2-methylpentane. So again, the longest chain, the parent, has 5 carbons. So 1, 2, 3, 4, 5. On carbon 3, we have an ethyl group. Looks something like that. And on carbon 2, we have a methyl group. There you go, done. And the next one is 1-cyclopropyl 3-methyl-cyclopentane. So this one, the parent is cyclopentane. So we're going to have a cyclopentane, looks something like this. And on the first carbon, we have a cyclopropyl. That's got 3 carbons in it. And then on the third carbon, we have a methyl group, like that. There you go. So what is it? 1-cyclopropyl 3-methyl-cyclopentane. Good. Okay, so now that we got that, let's tackle some Newman projections. So so if you're asking me, does it matter if it points like this or like this? Is that what the question is? No, it doesn't matter, because remember, there's free rotation around a sigma bond. Right? These bonds can rotate right? Anyway, so I could put this bond, I could put this one, pointing up like this. It wouldn't matter. There's always free rotation around a sigma bond. Yep. All right, let's take a look at this one. It says draw a Newman projection. Okay, so the viewer is looking down this carbon-carbon bond like this. So if we use a blue dot in the front like this, and then we have the red, this will be the carbon in the back, like that. Okay, so what is the viewer seeing? Well, going straight down, there's a chlorine. In the back, going straight up, there's a methyl group. CH3 for that. You can see the wedge is the methyl group that's going off to the left. So I'll put a methyl group over here, and then there's a hydrogen that is not drawn. And remember, this is a bond line structure. So this hydrogen here is not drawn in, but we put it in. We don't leave it out of the Newman projection. So our bromine is going to be on the same side as that proton. So we'll put our bromine here like this, and then there's another hydrogen, which is not shown because it's a bond line structure, but again, there's another hydrogen. There we go. So now we've included it. So there you go. There's our Newman projection for that guy. Exact same exercise for the next one. Here's the viewer. Okay, there's the eyelashes. So what are we going to do? This time I'm not going to color code it. I'll just have my dot in the middle. I have my circle around like this. So going straight down, you have a methyl group. Off to the left, you have a chlorine. And off to the right, there's a hydrogen, which is not drawn, but this is a bond line structure. Then going straight up in the back, you have a chlorine, which is in the same plane as the methyl. Right? Sorry, chlorine, not a chlorine. There we go. Then we have the bromine, which is going to be on the same side as the chlorine on the left-hand side. And then we have the methyl group, which is going to be over here like this. There you go. So there's our Newman projection. You can see that it is in the staggered conformation. Let's move on to the next one. Draw a Newman projection for the following compound. So again, imagine our viewer is looking like this. So we have our carbon in the back. We have our carbon in the front. So going straight up, there's an ethyl group. I'll just draw it. It's a bond line structure. There's going to be a methyl group coming down here. And there's going to be a hydrogen, which is not shown in the structure. In the back, there's going to be another ethyl group. Let's put it like this. Then there's going to be a methyl group over here. And then we have our proton, which is not shown, which is going to be going off to the left like this. Okay, so remember, there's a proton here that's not drawn, and there's a proton here that's not drawn, but we can't leave them out. The next one, number 12, just asks us to draw the lowest energy conformation. Looking down the carbon 2, so this is carbon 2 and 3 bonds. So if we imagine the viewer is being looking down like this, so we want to make sure to minimize gauche interactions. And so when we do that, we're going to end up with something where we have on the first carbon, we've got 2 methyl groups. So, and then we've also got a hydrogen, which is not shown. And then we definitely don't want to put this methyl group here, right? That would be the worst place to put it because then you'd have 2 gauche interactions. So all we have to do is avoid one of those because you can't avoid them completely. And so when we do that, I'm just going to put it, so that you have, we'll draw it in such a way that, I don't know, it doesn't matter, that the methyl group will be anti to one of them and gauche to the other. So I'll just put the methyl group up here like this, and then we've got 2 hydrogens, one like this and one like this. And that way, we only have 1 gauche interaction. So that would be the lowest energy conformation. The next one is really just practicing putting in your axial and equatorial hydrogens. So remember, if 2 groups or 2 lines are coming towards each other and they're pointing up, so you see how these are pointing in an upward direction, right? That means that that would be an axial position. So if it goes axial and up, then the next one is going to be axial and down. The next one's going to be axial and up. The next one's going to be axial and down. The next one's going to be axial and up. And the next one is going to be axial and down. If I go back to that carbon in the top left, if the first group is axial and up, it means the second group is going to be equatorial and down. On this one, the group is going to be equatorial and up. Oops, I guess I could have drawn it more parallel. It's going to be equatorial and up, like this. I still don't like that. I think it looks better like this. Here we go. The next one is going to be equatorial and down, like this. The next one is going to be equatorial and up, this. The next one is going to be equatorial and down, so it's going to look something like that. And the last one is going to be equatorial and up. So remember, they alternate up, down, up, down, up, down, and equatorial and axial alternate as well. So again, this, you just have to practice it to get good at it. Practice. All right, next one says draw both chair conformations or conformers of the following compound. So draw a chair, something like this. There's a chair. Draw another chair. Looking something like that. Okay, good enough. So let's imagine that the hydroxyl is going up and axial in the first one. That means it would have to be up and equatorial in the next one. And there you go. And if you want to figure out which side is the equilibrium going to lie to, well, it's going to lie to the side that minimizes 1,3 diaxial interactions. So it's going to lie to the right, because here you would have 1,3 diaxial interactions with this proton and with this proton. The next one says draw the most stable conformation of 1-ethyl 3-isopropyl cyclohexane. So they don't tell us anything about whether they're cis or trans, but we have a 1-ethyl, and then we have a 3-isopropyl. And so what would be the most stable chair conformation? It would be one where both of these are in the equatorial position, right? So that's all it's asking for. So most stable, it doesn't tell us whether they're cis or trans, so we'll just put both equatorial. So we'll draw our chair. And again, it doesn't matter where they are. We'll put the ethyl group as being equatorial like this, and then we'll put the isopropyl group as being equatorial like that. There you go. As long as both are equatorial, here I put them both equatorial and down. You could have put them both equatorial and up. It doesn't matter. They just both have to be equatorial. The next one asks you, which one is more stable? Now, you can try to draw the chair conformations of all of these, but there's an easier way to do it, okay? Let me coach you on this one. Let's start with number 2 first, okay? Because both of those methyl groups are on the same side. If this one is up and axial, then we know that's not stable because there would be 1,3 diaxial interactions. We know that if you had a methyl group going here, let's just say this hydrogen, could do better than that. If this hydrogen is pointing up, it must be up and equatorial, which tells us that this methyl group is up and axial. Okay, so if they're both axial, that means I could also have a conformation where they're both up and equatorial. So up and equatorial, and up, and equatorial. So that means there's a possibility of both of these being equatorial. In the first one, there is no possible way that both of these could be equatorial. Okay, it's impossible. If one is axial, then the other one has to be equatorial. Let me explain. If this one was up and axial, okay, that means that this hydrogen is up and axial, which means that this hydrogen is up and equatorial, which means that this group is going to be down and axial. So, oh, sorry, did I put it wrong? I put up and axial, up and, sorry, my mistake, up and equatorial. So that means that this one would be up and axial. Sorry about that. Here's my eraser. Up and axial. So that means that this group would be down and equatorial. So that means if one of them is equatorial and one of them is axial, no matter how I flip it, then the other one becomes equatorial and the other one becomes axial. So no matter what, you always have something in the axial position for number 1, whereas in number 2, you can have both substituents in the equatorial position. So let me just draw number 1. So if we draw number 1, let's say we have something that looks like this. If we have one group going up and axial, like this, in the third position, that means that the group would be going down and equatorial. So if I flip the ring, then this would become equatorial and this would become axial. But in number 2, if I have this group, going up and equatorial, then this one has to be up and equatorial as well, okay? I can flip it so they're both axial, but again, this is the most stable conformation, so the answer is going to be number 2. All right, the next one is, are the two substituents cis or trans? Cis means they're on the same side of the ring. Trans means they're on the opposite sides of the ring. Well, you can see that this group is, down and equatorial, and this group is down and equatorial, and so therefore they are cis. They are on the same side of the ring. They're both pointing down. The next one is something I don't ask a lot of, but it's just asking you to draw a wedge and dash structure of the following Newman projection. So if I imagine this dot as being, I'll use red for the dot, and if you imagine this blue circle, okay, so you imagine you're looking at it, right? You're standing right here, okay, looking at it going straight on, but then you turn it to the side. What's it going to look like? So if I draw the bond between the red carbon and the blue carbon, and again, I'm just color coding these for instructional purposes only, okay? You'd have a methyl group in the plane. You'd have an ethyl group in the plane. You would have the this methyl group going back into the page, the screen, like this, and then you would have this methyl group coming out towards the screen like this. So if you're struggling with this one would be this one, and this one would be this one here. Anyhow, so with the next one, it asks you to balance this redox reaction. So what do we need? We need the molecular formula for the hydrocarbon, and this is C5H12. Okay, so that's our starting material. So if you're ever asked to balance a combustion reaction, so this is a combustion reaction, you take a hydrocarbon plus oxygen, and you end up with CO2 and water. This is a combustion reaction, which is a type of redox reaction. Always balance the elements in this order. Start with carbon, do hydrogen second, and oxygen last. So we have 5 carbons, we need a 5 in front of here. We have 12 hydrogens, so we need a 6 in front of here. We tally up the total number of oxygens. We get 10 plus 6, which gives us 16. So what times 2 gives you 16? The answer is 8, and we are done. So remember, always do it in this order. Number 1, balance your carbons. Number 2, balance your hydrogens. And 3, save the oxygen for last. What's the relationship between these two compounds? Well, they're completely different because this one is C5H12 and this one is C5H10. So they are not isomers whatsoever. So these are completely different compounds. This one is an alkane, and this one is a cycloalkane. Alkane. And if you remember, alkanes, an alkane has the general formula CnH2n plus 2, whereas a cycloalkane has the general formula CnH2n. The next one, draw the ring flip for each of the following. Okay, so if this is our lead carbon, then we'll flip the ring like this. So if the tert-butyl group is going up and axial, in the next compound, it's going to be going up and equatorial. So we'll have something that looks like this. There we go. The methyl group is up and axial, and so now it's going to be up and equatorial, like that. This one, again, if this is our carbon here, I'll just move it down here. So if the chlorine is going down and equatorial in the first one, it has to be going down and axial here. Then you go 2 carbons away, and you have a methyl group going up and axial, so it must be up and equatorial. In this one, and then you have a chlorine going up and equatorial, so it must be up and axial. You can do better than that. Up and axial in this one. The next one, again, you have your fluorine, which is up and axial, so it must be up and equatorial here. So we'll draw it going up, equatorial. The hydroxyl is going up and equatorial, so it must be up and axial in the next one. And then the fluorine is going down and axial, and so it must be down and equatorial. And this one, there you go. All right, and the last one is name this bicyclic compound. Is that a beast or what? Okay, let's see if we can figure it out. The total number of carbons. So if I highlight the bridgehead carbons, I have this one and this one. I'm going to start with the biggest bridge. You can see the biggest bridge has a total of 1, 2, 3, 4 carbons in it. Right, there's a 4-carbon bridge here. Then we have a 2-carbon bridge here and a 2-carbon bridge here. So maybe I could color code those. This is 2 carbons and this is 2 carbons. So we're going to go through the one with 4 carbons first. And so we should start numbering where the blue highlighter is. because then we're going to give that first methyl group the lowest possible number, which is 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like that. So now we have a 277 trimethyl. So we have some kind of 277 trimethyl. Okay, and this compound is some kind of bicyclo. And there's a total of 10 carbons, so it's some kind of bicyclodecane. And if we look at the bridges, we have 4 carbons in this bridge, 2 and 2. So we have bicyclo, 4, 2, 2, decane like that. So this is 277 trimethyl bicyclo, 422 decane. So if we put it all together, there you have it, folks. Okay, so these are the kind of things that you're going to want to practice before tackling quiz number 4.